So I thought a topic that would be fascinating to start with today is about shoe tying. So no, I would never dare to do something like that with you. No, it's really a pleasure to be back here again. And Michael's right that, this is, for me, an event that I look forward to. And I think this is the third time I've done this particular event. And it's fun. I don't think, if you only go to the KNIME user group meetings and you don't go to other conferences, I don't think you realize what a gem you have with this kind of conference, with the quality of the talks and the interaction, and just the interaction between people who are coming is really something quite remarkable here. So I'm glad to see it grow and continue to do better and better each year. I'm going to be talking about target shuffling, but I'm going to be using it in a little different way than it was intended to be used. But that's not unusual, because I do that a lot. I'm going to talk about variable importance in particular, along with target shuffling, and why? Because, as I said, this is something that's bothered me for a long time, for decades, and I'm old enough to say that it's bothered me for decades. This is my fourth decade of data mining, back to the 80s, and it's really not that hard. So I thought those two things might be interesting. Okay, and so I'm going to dive right into, when we're thinking about variable importance, what things are we usually thinking about? And I'll start with a classic linear regression. So when you see a linear regression model, this is what you usually are thinking about. This is very simple, just 4 inputs. And each of them has a coefficient, and you look at the coefficients, obviously, and which ones have a greater magnitude, and you're thinking to yourself, okay, were they normalized first, and all those things. But let's assume that was all done properly. And the one with the biggest coefficient, you think, okay, now that is the biggest driver of this particular model. So that's pretty simple, pretty straightforward. Then you get to decision trees. And why do people love decision trees? It's because they're so easy to interpret, right? So you go to a decision tree that looks like this, and it's a nice split. This data that I'm using is a donation data set. So if you want to know who's going to respond to a mailing, you look and see how big their last gift was, and you get this nice little simple tree out of it. So that's great. But what if your tree doesn't look like that, but it looks like this? Now, I'm only showing you a little piece of it, because in the KNIME viewer, there's the entire tree, and you can barely see, if you've got especially good eyes, the gold box around what part of the tree you're looking at. Now explain that to your boss, right? And they're going, there's no way. So trees are great when they're simple. They're awful to explain when they're really deep. And then you get to neural networks. Neural networks. How do you explain a neural network? So, and to be honest, I actually took a picture like this once for a bank, explained it to them in a way that they checked the box and they said they would deploy it. So it is possible, but it's not particularly easy to do, explain what all this stuff really means and which variable is driving the predictions. Again, that's what we're trying to get at. Or you could unlock the covers even more in a neural network. This is the PMML, and you can get down the individual weights and look at those. No, we don't want to look at that stuff. Or even naive Bayes. Naive Bayes, it's a simple model, right? Very simple. It's just chopping up the inputs, comparing them to the outputs, and you get all these nice percentages and counts for all the values. Which of the input variables is driving the model predictions? It's not so easy to do, even with something simple like naive Bayes. Support vector machines. Here's what the support vectors look like. They're all right there, laid out for you in plain mathematics. And this is only 6 inputs in this model. Explain that to your boss. Not easy to explain. So then what do a lot of the software vendors end up doing? They will do something like this. They'll say, okay, well, we know we can't explain them directly, but we can get the gist, right? So we can get the gist by doing something like computing a sensitivity or an importance score. So for this particular model, this neural network has this list of inputs and these sensitivity scores. How they're computed, I have no idea. I actually know the software tool this came from, and I know it really well, and I used to train people on it all the time. I have no idea how they computed the score. So people used to ask me about that, and I'd say, well, just treat it as kind of a relative measure. Higher is more important, lower is less important. So you could do that. Or in the one of the nodes I really like in KNIME, the Ensemble node, you get a little more of a sense for what's going on, because this is a random forest model that I built here, and it shows you in order, I sorted it in a particular way, all the variables that are candidates for the model, and which one was used the most often in the root split. So that's the one that when it was available, because it was available as a candidate 20 times, 19 of those 20 times it was the winning split. So that's a decent indicator that this is a good variable. That's one that when it's available, it's used most often at the top. Just because, for decision tree, all you decision tree people, just because it's the root split does not mean it's the most important split. And we could give counterexamples all day long about things that happen along those lines. Okay, so that's just to give you some motivation. Why do we think about variable importance and why the algorithms themselves don't really help that much here? It leaves us scratching our heads. So what's going on? Let's try to figure it out. So the outline, I'm just going to talk about classical variable importance, the linear regression models, just to give you a sense, the things you already know undoubtedly, to lay the groundwork. And then we're going to do two hacks. One is using the linear regression model statistics themselves to assess what the relative importance of the variables are. But more importantly, we're going to go and use target shuffling. So let's talk about the data. So if you're going to do this, what's that old physics joke? You first assume a spherical chicken, something like that. So we're going to assume a nice spherical body of data, something that's really easy, something that we know is going to work, something we understand. So we just take, using the Gaussian distributed assigner node, which is what I use for this, created a three-input data set with a target variable, and the target variable equals 0.5 times variable 1 plus 0.2 times variable 2 plus 0.3 times variable 3. Everything's normally distributed, everything's super easy, everything should work just the way it's advertised. And here's what you get out of the model. Now, I'm actually happy about that, because here's the formula, and here's what the regression model finds. So at least we can check that box, right? So now we know it works. Okay, so that makes perfect sense. And here is just a little picture. If your boss likes pie charts, some do like pie charts, so that's fine. I'm okay with that. I'm not a big pie chart fan. Okay, so now I'm going to break some rules. I know I'm breaking rules. I know I'm going to do things which, for you statisticians out there, you're going to kind of squint and wonder why I'm doing it that way. But run with me on this. Play with me a little bit. We're going to look at the t-value that comes out of the regression score. And I'm going to sum them up and compute the proportion of the t-value that this variable takes up. Okay? I've never seen this documented in a book, but it was fascinating enough that it does work about the same as the coefficients. Okay? So I'm telling you this for a specific reason. We're going to use this again later when we're doing some other computations. So that's the t-value proportion approach. Another thing we could do, taking one step further, how much influence does each variable have? Well, you could figure that out. You could compute the influence of a particular variable by looking at the weight times that variable itself, just all by itself, not in the context of the model, and see how much of the target value that predicts. Okay, so now we've got three pieces, the influence of variable 1, 2, and 3, and we can see how much of the target value it predicts, and then compute, just like with the t-values, compute the proportion of the prediction that comes from each of the variables. Average that over all the data, and you get kind of a new proportion. And that looks like this, which is exactly what it should look like, right? Because on average, the proportion for every piece of the regression model should be comprised of the average weights. Because what do the weights mean in a regression model? The weights are the average influence of that variable across all the data, which is a reason I don't like weights, because averages of anything smear out. They get rid of all the interesting stuff, right? What's that book, The Flaw of Averages? If you've ever seen that book. If you haven't, it's a fascinating read. It's called The Flaw of Averages, and he's got a quote in there. It says, averages on average are wrong, okay? Which, of course, is true. Okay, so now let's do this with neural networks, right? Let's break it up, every term, let's figure out the influence of every single weight times input for the neural network. Or for a support vector machine, no, there's no way we're going to do that. We're going to look at that and just scratch our heads and give the duh look like our friend over here. So now let's do another way. So this is the YACK way. This is yet another creative use of KNIME. I do have a reputation of using KNIME in odd ways and using it in ways that were not envisioned by the developers, which is fine. I'm okay with that. So this is yet another way to use KNIME in a way that I don't think was envisioned. Target shuffling. Now that brings us to target shuffling. So if you haven't heard more about target shuffling than just what you heard today, I'd strongly recommend you can search for this particular paper online from John Elder, who is the one who really reintroduced the idea back into the common literature. And in his Peril of Vast Search and How Target Shuffling Can Save Science, it's a fascinating set of case studies on using target shuffling. Here's the URL. If you don't type fast enough, you can just ask me and I'll send it to you. Here's one of the problems too, even with linear regression. Okay, now I'm taking off my, I don't wear a statistician's hat because I'm not a statistician. But if I did, of course you want to pay very careful attention to the inputs. Transform the inputs in the right way so that the relationships between the input and the target variables are right. You've got that normal distribution with constant variance across all values of the input variable related to the target variable. Data miners, we don't really care, right? We just throw it in and let the regression model do what it does, and it still works amazingly well, even when we violate all the assumptions. So we have data that looks like this. We've got some heavily skewed, practically a spike, other heavily skewed data, negatively skewed data, ordinal data. We've got this one, which looks pretty good, and then you've got dummy variables, which none of these, except for perhaps this one, are really right. But we're just using them anyway, which of course will distort the coefficients, which of course will distort the t-statistics, which of course will distort our measures, all our common measures of which variables are more important. Okay, so we have to be careful of all those. That's why I wanted to show you this particular chart. So here's the target shuffling node in KNIME, and the principal use of target shuffling node is to shuffle the target variable. John Elder's work on this is saying one way to guard against overfit or to measure how much you're overfitting a model is to shuffle the target variable randomly, so you're detaching it from the record that it originally came from. Fit a model with a shuffled target variable and see how well it does. And if your new models with the shuffled target variables, which you've detached it from the original patterns in the data, if you've shuffled the data, you shouldn't do as well. And if you do just as well there as with your real model, then you know you've done something wrong, because a random model is as good as your model. Okay, so that's the John Elder's idea. Now, I'd like this idea for what we're doing here, because now we have a way not to shuffle the target, but let's shuffle the inputs to measure variable importance. Okay, so what do I mean by that? What I mean is we're going to randomly take one variable, shuffle it, all the remaining variables stay the same, and the target variable, of course, is the same, but we're not caring about the target variable anymore. We just care about the inputs and how it flows through the model. Okay? So when we score the model, you've got all the inputs, you're predicting the outcome variable from the model. Now we're going to take one of those variables, scramble it, and run it through with the scrambled input. But you don't do that once. You do that 50, maybe 100 times. So what then you get is for every record, you don't get one score, you get 50 or 100 scores. You're getting a distribution of scores related to what happens when you scramble that input. Okay, so now think, what does that mean for your predictions? If the spread of that shuffled distribution is really big, do I have that up here? Yes. If the standard deviation is big, that means that variable has high influence in the predictions. If the distribution, if that standard deviation is really small, if it's 0, that variable is irrelevant. It doesn't matter how you detach it. If it's low, then it has less influence. So that's the idea we're trying to get at. Now, why do we do it like this? Why don't we just take all this, and this is a common way people get at this idea. What if you just froze all of your inputs at the mean or the mode and shuffled one variable and just scrambled one variable? That's the way a lot of these variable importance algorithms work. You just move one of the variables by some random amount plus or minus 1 or 2 standard deviations, keeping everything else fixed. Why isn't that a good idea? Because the patterns in your data are not average. This way, with the target shuffling approach, you keep all the patterns exactly the same way as they were in the data originally. The interactions are the same as they were originally. And all you've done is detached one of the variables at a time. Okay? So I'm hoping I'm making the case why this idea, random experiment, is a real good way of getting at this. So I know, Bernd, I told you I wasn't going to show this, but I'm going to show it anyway. The inner loops. So we loop on the shuffled inputs, and let's say you've got 30 inputs to your model. Here's that shuffling loop. We're at the target shuffling, and then I'm joining that up with the original data. So you've got the shuffled variable, like n-gift-all, join it up with the rest of the data, so now you've got all your inputs with one shuffled column, and you run that through the predictor. And then you do that again and again and again, your 50 or 100 experiments. And the outer loop is how many times how many variables you're going to run this on. So you run it on, let's say you've got 30 variables, shuffling 50 times each. You just do this double loop. At the end of this inner loop, I'm grouping by the record number to get that distribution of model scores for that input. That's all that's doing. I'm going to compute the standard deviation for every record when I shuffle that variable. And this is getting a little more detail on the shuffling input. Oh, wait a sec, I shouldn't use this one, Michael. This one has that Java snippet node there. Let's take that out. Let's use a target shuffling node instead of using the Java snippet. So this is just showing the inner part of that. Just one input at a time on the top branch, all the other inputs on the bottom branch. And so this is what the shuffled data looks like. For all the variables, except for the shuffled variable, it's a constant. Remember, we're keeping all the other variables as they exist in their original data. So for every record, it's the same values that you saw before. For the shuffled variable, you're scrambling it up. Another good thing about that, the scrambling it up, if you've got really bizarre distributions in your input data, I mean, if it's normally distributed, it doesn't matter, right? You can just do a random normal scrambling yourself. But if your data is heavily skewed, if it's multimodal, or if it's binary and you want to get the right proportion, all this stuff happens automatically by resampling the column itself. And that's one thing I really like about the approach. And then you get some shuffled distribution out of this. And then once we get the shuffled distribution, collapse it. Let's say we had 10,000 records. You get distributions for every one of those 10,000 records, what the model scores are. Collapse that down to a single metric. Now, this is where it gets kind of antsy. So how do you collapse it down? You've got distributions, you've got standard deviations, and then what I did, and this is a research work in progress, I fully acknowledge, I computed the mean of the standard deviations as you collapse all those records in the file. So you're finding what is the average amount of spread you see when you shuffle an input. That's all you're trying to measure there. Okay, so in this case, the mean is 0.05. The standard deviation for that particular record is that. And then when I shuffle on all the variables, this is the regression problem that we're looking at before. Voila, you get the exact same results we're seeing in the beginning on the easy data. So again, that makes you feel good. At least I got that part right. So at least it's believable, it's plausible that the shuffling approach could do something that is reasonable. Okay, well, what happens on realistic data? So here's another data set. This is that donation data set. I just use 4 input variables here. Last gift, how much they gave the last time they gave, how many gifts they've given in their lifetime, and some recency metrics, like how much did they give recently and how frequently do they give as measured recently. Here are those 4 variables. weird distributions, which will be a problem. You do a scatter plot matrix, and it looks really bad. This just does not look very good. So one of the things I did with my workflow is I normalized everything so that I could put everything on the same scale for some of the algorithms that really care about this, like nearest neighbor would care what the distributions are, or even support vector machine or neural network to some degree would care. So I do this, and now your data, your 4 data fields look like this, much nicer. But the important thing is this: what do you get? Build your simple regression model, and I showed this at the very beginning. Last skipped has a huge coefficient, huge proportional coefficient, and if you were to just take the coefficients, take the absolute value of the coefficients, and just kind of get what's the general proportion, you get this kind of look at the data. Last skipped is the biggest driver. If you use the t-value approach, you get this kind of metric. So according to the t statistic, or the t-value here, you get last skipped is delivering approximately 2/3 of the value of the target variable on average. Okay? So now what happens if you use this direct proportional method? Remember I talked about the direct proportional method which you can do with linear regression. Look at each individual term, the weight times the input variable, how much of the target value does it predict, and then average that proportion over the entire data. And interestingly enough, you get just about the same thing as you get for the coefficient approach. However, the random shuffling, the input shuffling, does almost exactly what the t proportion does, which is why I'm saying, even though it made me really uncomfortable to do that, what's the proportion of the t value that's coming from each variable, there seems to be some merit in that. Now, some of you may have done the math, and maybe you can figure out the math and why that's the case. I haven't done that yet, but I'll leave that to somebody to experiment with, and next year at the conference you can present your findings, right? Okay, so now let's go back to our harder problem, and what do we get? For linear regression, last skipped was about 2/3. For the multi-layer perceptron, for the neural network, it was a little bit less. The interesting thing about this to me is that one of these variables, this dummy variable, RFA2A, actually was used more in the neural network than it was in the linear regression model. About 13% influence in your final predictions, compared to here it's 9.8%. RFA2F, which was the ordinal variable, was used a little more. So that's all kind of interesting stuff. The thing that's cool about this, though, I just ran the same code, the same target shuffling approach with neural networks and regression models. So the motivation was from regression, because it's telling us the same story that we're seeing using saner methods with regression modeling. But it's doing a similar thing with the neural networks, giving us confidence that the shuffled approach is really doing something interesting even for the neural networks. That also means we could do that exact same thing for support vector machines, decision trees, random forests, anything, any model, because all you care about to build these shuffled analyses of the data are the inputs, which of course we have, and the prediction column. You don't need anything else. You don't need to know anything about the model itself, just the relationship of the inputs to the target. Let me mention one thing. How much time do I have? Okay. I'm going to mention one other thing briefly. This is another thing that's always bothered me about these metrics. I'm going to go back a slide, so for those of you who are taking a picture, I'll come back to this, so don't worry. These metrics for linear regression, multilayer perceptrons, and random forests, and you'll notice random forests and the neural networks are about the same, which was interesting too. These metrics are interesting, but these are on average metrics describing the influence of each variable on the target. And what did I say before about on average metrics? I don't like on average metrics. They're great to describe things on average, but they don't tell you the whole story, because of course whenever you average something, you're losing information in order to summarize it more concisely, right? What would happen if instead of computing an on average shuffled variable importance, we broke up the target variable predictions into deciles? And we looked at, for each of those deciles, what is the influence? Which variables have the most influence in the top decile, the second decile, the third, fourth, fifth, all the way down to the 10th decile? Or you could do demi-deciles or whatever, or percentiles, whatever your desire is. So why would that be interesting? Think for a second. I'm going to back up to a picture, if I can go back far enough. Look at this variable here. Dummy variable, very small percentage for this DRFA2A variable. Very small percentages of ones. On average, will that be a strong predictor? And the answer is probably no, because the counts of the ones are not high enough for it to participate enough in the predictions for it to really show up. However, what if this was a rock star dummy variable that only showed up in the top decile? Then this will show up in the top decile shuffled performance, and it'll say this is a great variable in the top decile, even if it's irrelevant the rest of the way, right? So breaking up into deciles can tell you more of the story, what's going on. Because a lot of times when I'm doing marketing kinds of problems, what someone's likely to purchase in 7 days, which is something I build a lot of, those kinds of models. It's interesting, but we're very rarely operating on the entire population. We're really only going to make decisions on a small subset. And if we can identify which variables are driving that subset, it'll help the decision makers understand why they're seeing the behavior they're seeing. Okay, so now let me go back forward and show you what we find from this. So here is deciles and of the predictions, and I want to show you these variables related to the deciles. Here's last gift. And here is its shuffled influence across the deciles, trying to predict how much somebody will spend if they are re-engaged. And you'll notice that at the upper end, it's very influential, but down at the bottom, when the last gift was small, it is not nearly as influential. It's much more influential at the top end. The same thing is true with how frequently they give. The larger it's much less influential at the low end. Same thing with n gift all, and RFA2A has almost no influence at the bottom end. So the point here is simply this, that when you're measuring importance, on average metrics are great. On average metrics tell you the gist of the story, but then when you start splitting it up into smaller subsections, then you can really get at the core of the story for each of the subgroups. Okay, so let me close it off with this. What is so good about what I'm calling now input shuffling? Because we're not shuffling the target anymore, we're the input variable. And just as an aside, Michael, I was joking about the Java snippet node, but of course you could do this in KNIME without the target shuffling node. I mean, you could create a random number, and then you could sort by that random number, and grab one of the variables, and then append columns to get the randomly scrambled input variable in there. But the target shuffling node makes it so much easier. It's so much nicer just to put one node in there and then have to build up 3 or 4 and throw it into a meta node. So why is target shuffling good? It works for any input distribution. Doesn't matter, because that's the distribution that's in your training data. That's exactly what you can use. It works with any algorithm. Does not matter. It's literally irrelevant what the algorithm is. It measures the importance based upon the input variables, the remaining input variables, as they exist naturally in your data. You're not making a simplified assumption about what's the mean of the distribution, or you're not scrambling it through, according to some probabilistic density function that may or may not exist in the data. And you can use any metrics. I was using the metric of standard deviation for each record to measure how influential a variable was. But you could do a lot of things. One of the things I was experimenting yesterday with Bernd was I was computing the ROC score, area under the curve, for a shuffled version of the data, and then looking at, for every variable, what's the distribution of the ROC scores? How much is that influence? And that's a perfectly valid metric as well. So you're not tied to one metric. It depends on what you are most interested in. Now, why isn't it as good? Well, if you've got a lot of inputs and a lot of data, it could take a while to do. So models that may take a minute to score or tens of seconds to score, of course, you're going to be, for every input in your model, you've got 50 or 100, let's say you have 100 inputs, and you're going to do 100 random shuffles, that's 10,000 experiments. So it's going to take a little longer per model. And there's no statistically defensible metric to use. I mean, I just kind of made it up as I went along. Now, to be fair, I think I could defend what I was doing, showing how it matches back to the regression t-value assessment, to say that it actually is doing something that makes sense, that's reasonable. But I can't defend what I was doing from a textbook or from a statistical perspective. Okay, just in conclusion, the coefficients aren't good measures. Those coefficient values for regression models are fine for on-average influence if you've satisfied all the assumptions in your regression model. That's fine. But once you deviate from that, or I should put it more precisely, the more you deviate from the assumptions, the less those coefficients will measure what you think they're measuring. So if you're not of the mindset to go through and push all the data into that regression box, get all those inputs. Look, I made a career in consulting out of going up against statisticians who spent months pushing the data into the box to make the data just right. When marketing departments would come to me and say, Dean, we can't wait 2 months for this model. Can you build it in a week? And say, sure, I can build it in a week. Because I'm not going to care about the distributions. I'm going to use non-parametric approaches or distribution-free approaches instead of trying to force it into this framework. So anyway, the coefficients, just beware of coefficients. And some models, I dare say most models, don't have coefficients you can use. With a neural network, could you use them? Yes, you could use them if you wanted to. It is true, I've actually done that before, loading up all the coefficients into a spreadsheet and measuring influences and going through all that in detail. I've actually done the computation of partial derivatives in a neural network to try to figure out what the influence. You don't, believe me, you don't want to do that, unless you're really weird like I was. So don't do that. But using target shuffling, we can generate these sensitivity scores through random permutation. Random permutation is a tremendously powerful and valuable approach to finding out how important things are. Not just with this. I'll tell you another place I'm going to use that I have used, not specifically the target shuffling variable, but I've done that same idea, is in computing how stable model scores are by scrambling the data, shuffling the data, taking a random, like a bootstrap sample, and computing what the model score changes are as you resample over and over again. Random permutations are tremendously powerful ways of getting at influence and sensitivity scores. So with that, I think, and I talked about breaking things up into deciles. That is also a valuable way to do this, to get at the influence at the different ends of the proportions of the distributions. So this is something, I've got the meta node to do this. If anybody wants, I'm happy to share it. Bernd has it now too, if you want to experiment yourself. But it's really not that hard to do. You can do it yourself. I would commend it to you to give it a shot to see with your neural networks, if you want to know what is driving the prediction, this is a way to get at that answer. And I think at that, I will call it quits because the beers are waiting.